think we can start with our first speaker of today, which is Michalea King. She just finished her PhD at the Byrd Polar and Climate Research Center, and I think she will be presenting work from her PhD, which was about variabilities in the velocity of Greenland Outlet glaciers. And like I said, she just finished her PhD, and she will be working as a postdoctoral fellow at the University of Washington Polar Science Center later this year. Over to you, Michalea.
Okay, great. Thank you, Rebecca, for that introduction, and thank you everyone that is tuning in today. So as Rebecca said, I'm presenting work that was completed mostly during my PhD, but I will carry over some of these research themes into my postdoc. And today I'm going to be talking about how we can use high resolution velocity time series to understand how sensitivity to meltwater runoff varies across the ice sheet. So looking specifically at how outlet glaciers respond to meltwater and how that impacts their sliding speeds. So just as a primer, the Greenland ice sheet goes through dramatic changes in the summer months, especially on the surface. So there are really complex and widespread networks of meltwater ponds and rivers that form on a lot of the ice sheet. And some warmer summers, as much as 90% or more of the ice sheet will melt on the surface. And these meltwater ponds and rivers are increasing with elevation through time as well. And so why is that important to those of us interested in outlet glacier dynamics? Well, surface meltwater does not just change the surface melt mass balance, but it also impacts dynamics at the ice edge. So when we're talking about outlet glaciers, this meltwater can infiltrate into the subglacial system through crevasses and moulins and actually impact ice flow by altering how the ice flows along its bed. And so I don't want to spend a lot of time on this because it's something I'm sure many on the call already know, but essentially how we understand flow speeds in response to meltwater comes down to changes in the basal water pressure. So if we imagine this, a little cartoon here is an oblique view of a glacier. At the beginning of the melt season, we might have pockets of water, but it's overall a disconnected, inefficient drainage system. So at the onset of the melt season, when we add water, we expect this to rapidly increase basal water pressures because that water does not get readily evacuated. So at the beginning of the melt season, increases in basal water pressures correspond with increases in ice velocity. So we would be in this light blue zone here. However, as the melt season goes on, eventually these small channels that form grow and they become more consolidated, and eventually we form a series of really efficient drainage systems or large channels that readily evacuate the meltwater from beneath the glacier out to the ocean. When this happens, because that water is not pressing up against the ice because it's so easily evacuated from the subglacial system, we see that the velocities then decelerate. And so that would be more of this light blue region here. And so throughout this talk, I'm going to be referring to the switch, and that just refers to this change from acceleration to deceleration, or you can also think of it as the switch from inefficient to efficient drainage systems. And so for this work, I'm looking at velocity time series for all large outlet glaciers surrounding Greenland. And so this is about 230 large outlet glaciers, and the positions of those glaciers are shown along the margin here in the light teal colors. And so this is just one example. This is at Jensen Glacier, what a velocity time series would look like. And we're really taking together all the different data that we have. So that includes optical as well as radar data. The optical data is shown in black here, and you can see there's a lot of gaps in that. That's from gaps in the Landsat record. But beginning in 2007, with the launch of the TerraSAR Tandem X mission, we're getting a lot more continuous temporal coverage, because now instead of just having the optical data, which we can only get velocities in the summer when the satellites can actually optically see the ice surface, we can now get observations of ice velocity in the winter as well. And so because for this project, I'm really interested in getting a detailed look at how the seasonality of these glaciers change through time, I'm only going to look at the years after which we have well-resolved seasonalities throughout the whole year. So I'm only going to be looking at 2007 onward so that we don't include large temporal gaps. And so I have a couple criteria to include data in my analysis. First, a given year has to have an observation for at least 6 out of 12 months. Any less than that, I don't feel confident to say I can resolve this seasonality well if we're only having 5 out of 12 months with observational data. So it has to have at least 6 out of 12 years, or 6 out of 12 months of data. And then glaciers that only meet this condition 75% of the time are completely excluded. So if we have a glacier, for example, 79 Fjorden was one of these examples where there was just 4 or 5 years with the data was pretty sparse. I just excluded that altogether because, again, we just don't have enough data to confidently say this is the typical seasonal behavior at that glacier. So given those initial criterion, I then end up with about 120 glaciers. So a little over half of my initial sample size are included then in further analysis. And those are represented in the red dots on the left. And although I've decreased my sample by about half, most of the really large glaciers are still included. So the glaciers that I will go on to talk about in the rest of the talk represent about 80% of the total ice sheet flux. So we're capturing most of the glaciers that are really the big contributors to dynamic ice losses from the ice sheet. And so again, I'm going to take this 2007 onward record and I'm going to detrend the data, and then I'm going to stack each year to look at how that seasonality has changed through time. So in this plot, starting in the dark purple, this is 2007 through more present in yellow. This is just showing that seasonal variability in the velocity in each year. And so from that, those curves, we can get a mean seasonality as well as an estimate of the distribution around that mean. So this will give us that standard typical behavior at that glacier, as well as provide us with an estimate of how consistent seasonality is at a given site. And so I do this for all of the glaciers, the 120 glaciers that met the criteria. And what I found was that there were 3 main patterns that emerged from these typical seasonal curves. And these 3 patterns each suggest a different type of sensitivity to meltwater forcing. And I'll walk you through what each of those mean in a second. But I do first want to point out that there are other papers in the past that have looked at types of glaciers or categories of glaciers based on what their seasonal curves look like. Twyla Moon's paper in 2014 was one looking at 55 glaciers. And Saravijay's paper last year looked at 45 glaciers. And so there are other people that are working on looking at different types of glaciers as well. And so first, the category 1 glaciers are really what you think of close to a perfectly symmetrical acceleration deceleration. But even more importantly than the symmetry that these glaciers exhibit in their velocity signal is how closely aligned the velocity varies with the melt season. So going back quickly, the blue here, this is the velocity. Then if I superimpose the normalized trend in meltwater runoff, you can see that's here in the gray. And so what you'll notice is that the maxima of these 2 curves are really coincident with one another. So that means velocity peaks when runoff peaks. And similarly, once we reduce runoff or we reduce the supply of melt to the system, we also reduce the velocity as well. And so if we think back to when we talked about switching between inefficient to efficient drainage networks, this is really hard to say if these glaciers switch or not, because it could just be that these glaciers decelerate when the melt supply also is reduced. So there could be switching behavior, but it is not with a shadow of a doubt determined. So that's category 1. So if we look at category 2, again, focusing first on the blue curve, they accelerate at the start of the melt season. So they accelerate because basal water pressures are increasing, it increases sliding speeds. However, unlike category 1, which had a symmetric deceleration phase, these glaciers actually maintain high velocities well into the autumn and winter months. So this is suggesting that there is an inefficient drainage system at the start of the melt season that enables that increase in basal water pressures, but there's not that clear switching that occurs because you don't see that rapid deceleration accompanying these glaciers. And then lastly, category 3, also maintaining high velocities outside the melt season. But what's really interesting about Category 3 glaciers is that they actually decelerate at the very onset of the melt season. So it doesn't take much at all to switch these glaciers to where they form these efficient drainage systems and then rapidly decelerate. So again, usually within the first few days of the melt season, you see these glaciers blow out their subglacial systems and then decelerate rapidly. Another thing I want to point out is that because of the elevated velocities outside the melt season observed in Category 2 and 3 glaciers, this implies that these types of glaciers are perhaps better equipped to store water outside the melt season. So they're storing water more readily, and that's helping maintain high basal water pressures outside the melt season. All right, so to go into some results quickly, this is showing the distribution of the 3 different categories, Category 1, 2, and then 3 on the right here. And the percentages on the ice sheet in white, this is showing what proportion of the total flux of the ice sheet glaciers within that category make up. So Category 1 glaciers, again, that's that nice symmetric increase and decrease. That's about 1/5 of the total ice flux from the ice sheet. The largest category by volume by discharged ice is Category 2. So a little over 1/3 of the total dynamic ice loss from the ice sheet comes from Category 2 glaciers. And then Category 3, about 1/4 of the total flux. And what you'll notice is that there's no clear spatial pattern to where you can find each of the respective categories, other than the fact that only Category 1 glaciers are shown in the northernmost region. So if we're going really far north, we only see Category 1. But other than that, there's no real clear spatial pattern. So that suggests that there's maybe more local perturbations or local geometric conditions that drive these categorical differences. Right. And so I kind of spoiled the next question, but what we're then looking at now that we've resolved the different types, we've seen where these glaciers are found, I want to know then what is driving these categorical differences between type 1, 2, and 3. And so for this work, I've looked at several different parameters, several different variables, and tested differences between the categories. I'll list them here, but we're only going to talk about a couple today just for the sake of time. There's geometric conditions, so things like bed roughness and slope, the cross-sectional area of the outlet, so how large is the outlet this runoff will eventually come out to see through. Height above flotation, is the glacier really close to flotation near its edge, or is it actually very well grounded? As well as difference in the hydropotential gradients within each catchment. And then there's also environmental conditions. So how much runoff is within each catchment, as well as changes in the front conditions. We haven't talked about the front at all, but of course this is also going to impact the velocity signal, right? Changes at the front will propagate upstream, and this is also kind of convoluted in the meltwater signal as well. And so really quickly today, I'm just going to show some early results from changes in the cross-sectional area of the outlets, as well as looking at changes in front conditions and seeing if these can tell us anything about the categorical differences between our 3 categories. And so when I talk about the cross-sectional area, the ratio of the cross-sectional area between different categories, what I'm referring to is the ratio between the basin integrated runoff. So let's say, for example, this is Kangerlussuaq. If I integrate the total runoff within that catchment and compare it to the cross-sectional area of the outlet that volume of water has to flow out of, I want to get a ratio for that number, essentially saying how much water volume per exit gate area do we have at each of these sites. I hope that makes sense. And so if we compute this for all the glaciers and bin them into our different categories, we find that there's actually a significant difference between Category 3 glaciers and the other 2, Category 1 and 2, where Category 3 glaciers have over double the volume of runoff that would hypothetically pass through that outlet gate. So per outlet gate area than Category 1 and 2. So you can almost think of it like twice the flux of water that has to exit that catchment. And this is actually really interesting and kind of supports our earlier arguments about Category 3 glaciers, is because they overwhelm their system so early in the melt season, where that switch takes place really early on that it only needs a very little additional amount of melt to blow out that system and form these efficient channels. And I think part of that might be due to the fact that there's a greater volume per area of runoff that has to pass out these outlets, so that it's really easy to form these channelized drainage networks. And then secondly, I want to show you quick results from looking at how we incorporate changes in the front into this whole dynamic mix of questions. So of course, like I mentioned, changes at the front also have to be considered. It's really difficult to do this without having, fully coupled model, or at least a flow line model incorporating changes at the front as well as upstream, downstream dynamics, but we're going to at least try. And so one thing that I'm looking at right now is how often do these patterns of acceleration coincide with periods of retreat? So basically looking at how often is retreat also something we have to think about. How often is retreat also occurring during these periods of acceleration? And so this figure here in the black, this is showing velocity. This is at Hayes Glacier. This is in Northwest Greenland. The shaded areas of red, this is showing daily retreat rates. And then when you see green, that means the glacier is advancing. And then everywhere that you see the gray shaded bars, those are highlighting areas where we're both accelerating while we're also retreating. Essentially what I'm looking at here is a number to say, what fraction of the time do we have to also worry about retreat convoluting the signal that we're trying to extract about meltwater? And so I just highlighted areas where that's occurring at least half the time. So these you could think of as my problematic glacier sites, where there's more investigation that needs to take place before we can actually say it's a meltwater driven signal. And it's worth noting as I close up here that most of these glaciers are category 2. So again, we're looking back to the glaciers where they accelerated in the melt season, but then kind of slowly decelerated, or they maintained high velocities. So this is a question I'm kind of pondering now, is does the fact that these glaciers are sensitive to the front, does that mean there's no meltwater signal? Or does it instead suggest that changes at the front and the melt season are actually even more closely coupled at these sites, where you might see perhaps enhanced subglacial melting because of subglacial drainage that's kind of coupled with the timing of the retreat that then propagates more acceleration at these sites? I mean, this is something I don't know yet, but it's an interesting question I'm working on going forward. All right, I won't walk through these summary points, but essentially there are non-uniform changes across the ice sheet. There are categorical differences in geometry and environmental conditions that are starting to explain some of these categorical differences. And there's a lot more considerations that we need to think about with incorporating changes at the front into this whole puzzle as well. All right, so with that, thank you. And I'd be happy, I guess, to take questions at the end, correct? Okay.
Yeah, there are questions for you in the chat box, but yeah, other questions would be great to get at the end, I guess. Thank you so much. That was excellent. And I would suggest we just move forward to Will's talk. So we go from satellite observations to ground-based data. Will Harcourt is a third-year PhD student at University of St. Andrews, and he's working on developing a ground-based millimetre-wave radar for monitoring glaciers. And I know actually Will is he loves the Scottish landscape, running and cycling there. And I wondered if looking at the deglaciated area like drumlins and moraines and all that, if that made you go into glaciology, but we might find out. Over to you, Will.
Well, I don't come from Scotland, but it certainly makes me want to be a glaciologist even more. I'm sure you can see my slides okay? Yeah, cool. Yeah, so today I'll be talking about the development of a new radar sensor for glacier mapping. And this is a collaboration between, let me just change my pointer. Can I do that? There we go. Yeah, this is a collaboration between the Universities of St. Andrews and Aberdeen. I'm funded by SAGES and EPSRC for this work. And I'll be showing some results from Glacier in Switzerland in this talk. So I just want to highlight or say a big thank you to the Ice Grotto Cafe there who helped us during our fieldwork last summer. So just to kick off with a bit of motivation, the main driving force behind this project and to develop new sensors is the fact that we need high resolution measurements of loads of processes in glaciology, but particularly iceberg carving. And I've highlighted a time lapse of Helheim Glacier in Greenland, which shows the ice flowing into the sea and discharging icebergs, and punctuated by a retreat of the ice front from carving events. But then when we look at this process in ground-based time-lapse images, we can see that this process is really complex, and satellite images don't really do it justice at all. Therefore, we need better measurements of these types of processes to really understand how these glaciers are going to evolve in the future. I think this is neatly summarized in this quote down here at the bottom. A model is only as good as the data that feeds it. So we need better data, and to do that, we need better sensors. And in this talk, I want to try and make the case for millimetre-wave radar. And so here I've plotted frequency, so operating frequency of an instrument against atmospheric attenuation. And the key things to highlight in this plot is that in the red line, we've got a standard atmosphere attenuation, and in the green line, we've got atmosphere plus water content, so fog or clouds in this case. And in the high frequency region, the optical surveying region, so laser scanners, LiDARs, and cameras, as soon as you add fog or clouds to an environment, the attenuation increases so much, in this case by 3 orders of magnitude, that they become effectively useless. You can't use them in these environments. So many people use radar sensors instead to image glaciers on the ground from satellites. But as you move down through the lower frequency bands, you have another problem. Lower frequencies have lower resolution. So there's a trade-off here that we need to try and work out. And in this presentation and in my PhD, I'm trying to argue that millimetre-wave radar is an alternative solution to this problem. And millimetre-wave radar operates here between 30 and 300 gigahertz. So my PhD is all about developing millimetre-wave radar and trying to plug this gap, this knowledge gap. And the radar that I'm using in my PhD and in this study is the AFTIS-2 radar, which was developed here in St. Andrews. I've got a diagram here showing the radar system. We have the radar head and then Cassegrain antenna and a gimbal. Place it on a surveyor's tripod, and we position the radar system with a GPS. The whole system is powered by 2 12-volt car batteries, and we control the whole system with a power supply unit and control box. The specifications of the radar itself, it's an FMCW radar operating at 94 gigahertz, which has a wavelength of about 3.19 millimeters. The two-way radar beam width is 0.35 degrees, which gives an azimuth resolution per kilometer of 6.1 meters. The range resolution we set at 0.75 meters, and the maximum range is 6 kilometers. It takes around 50 minutes to image a 20 by 5 degree scene at 0.1 degree increments. And it's a reasonably heavy system, 40 kilograms, 2 car batteries, 46 kilograms. But once you break it down into its constituent parts, you can transport it in the field. So it's sort of field portable. And now to get into the guts, some of the results of this presentation. Here's a time-lapse image showing the radar system scanning across the scene. So what AFTIS does is it scans from left to right, up and down, and it measures backscatter along each line of sight. And by doing this, we can build up an image of the scene. And the main reason, so in the summer of 2019, we deployed the system here at Glacier. And the aim of this field was to try and gather backscatter data from glacial ice, because no one had ever published this before. But it's really fundamental data to try and understand how well a system performs in terms of remote sensing. And now to illustrate exactly what the data looks like. So on the map here on the left-hand side, I've got a map of Glacier. And this plot on the right-hand side shows one left to right sweep of the radar. So this is basically all just noise at one single elevation angle. But if I play this video, and hopefully you can see it okay. Yep, there we go. As we scan upwards through the scene, we start to see these bright bands appear in the data at each elevation angle. And this is just backscatter from the scene. And I guess the best way to try and understand what this means is that they're basically like topographic contours on a map. So it's really cool data to see this. And because they're similar to topographic contours, it suggests that we can build up digital elevation models. And this is the first thing I want to try and concentrate on, one of the biggest main data sets that you can get from this type of radar system. What we do is, so this plot on the top left-hand slide shows range profiles with AFTIS, the radar here at the 050 position. And each of these line of sights has noise, but we also get these terrain backscatter echoes, which are the bright bands we saw in the video before. And by applying an algorithm to find the range to the maximum power along each line of sight, we can generate point clouds like this. And this is a point cloud of the snout of Ron Glacier. So from here on in, we're just going to concentrate on this area here just for simplicity, and it's where we have the best data actually. And this point cloud here is just colored in with raw radar receive power. And from that point cloud, we can build up DEMs. So this is the first ever DEM of a glacier generated from millimetre-wave radar, which for me is quite exciting. And yes, it's just a DEM. It may not be the most exciting for anyone that looks at this kind of data, but it's actually really cool because it shows and it demonstrates that millimetre-wave radar can map glaciers and map elevation, which is really nice. And you can see and you can pick out some of the features of the glacier. So again, we've got the picture here. This box highlights where we're looking at. And you can see the valley sides here of the glacier. It picks out the icebergs quite nicely. We've got this area. This area here is actually, you could be forgiven to think this is snow, but I guess some of you may know this is actually our tarpaulin cover, which is draped over an ice cave. It's put over this area to stop it from melting out because it's a tourist attraction. It provides the economy to the local region. But I think this nicely illustrates the kind of data we can gather with this radar system. And next, to try and move on to trying to understand what we're measuring. So we've built up these DEMs, but the other side of the data that we can try and utilize is the backscatter data. But to understand backscatter, we need to understand what it is we're actually measuring. So what does a glacier look like? Well, a glacier is highly irregular. We've got so many different types of, lots of different melting regimes all across the glacier, making it extremely rough. We've got different debris contents, varying from the lateral margins, and here you can see there's lots of debris near the margins of the glacier. My supervisor perched on some sediment or maybe ice, I'm not quite sure, but nonetheless you can see that there's lots of debris here. And we've got these macro scale topographic features like crevasses, which change the angle of arrival of the radar, again alters the backscatter regime. So we need to bring this all together to understand what we're measuring. And this shows the raw radar receive power if we take the maximum power at each range bin. And it's sort of like a SAR image, so synthetic aperture radar image. It's completely different in the way it's measured, but it can be analyzed in the same way. And for me, this is a really cool image because it nicely shows a lot of the features that we saw in the DEM, but at high resolution because of the way we're measuring this particular scene. And you can see here in the left-hand side, we've got the valley sides, different kind of brightness levels or backscattered levels with the main ice body. We've got the icebergs in the proglacial lake and the ice terminus you can quite clearly delineate. This is interesting. Again, we're looking at the tarpaulin cover here, which is this region here. And it seems to me that the millimetre-wave radar signal was actually penetrating through the tarpaulin cover and imaging the crevasses below the tarpaulin cover. So it's quite interesting, not necessarily that useful in terms of glaciology, but just interesting to note that we're able to penetrate through small, thin layers of material. And again, we can see some crevasses up here. And it's actually quite a nice speckle pattern. And this talk is called The Opportunity of Millimetre-Wave Radar. If we can image scenes like this and get a speckle pattern out, there's potential here, if you have different images over different time periods, to implement some kind of speckle tracking algorithm. But that was the raw radar receive power. That is uncalibrated. So what we need to do is we need to find a way of quantifying the normalized radar cross-section, which is the main quantity of interest when we're talking about radar. And that quantity measures the area averaged backscatter for a given area. And the way we do this is we place these trihedral radar reflectors out in the scene, and we know the radar cross-section of this which is 20 dBSM. We use the radar range equation, which we've highlighted here as the radar model, put in the hardware characterization, so we know the transmit power, we know the antenna gain, we know the wavelength, put that all into the model, and we try to match that up to the raw radar received power from the reflectors. There's a big caveat here, because when you're imaging, you still have attenuation in the scene, and you have to try and work out what that attenuation factor is. It's not entirely easy because it's spatially different, but we need to find a number which is comparable for the time in which we were imaging. And for standard atmosphere, the attenuation would be 0.35 dBs per kilometer. But if you're imaging over a glacier where you've got lots of water going into the atmosphere from melt, evaporation, sublimation, more water vapor increases the attenuation. So we've increased the attenuation factor in our model. And when you do this, it actually quite nicely fits with the raw radar power from each of these reflectors. So these are CC1, CC2, CC3, CC4 as the corner cube placements. And now you can see that the data nicely fits the radar range equation model. And this is useful because what we do with all the parameters in that model is we use that to try and work out the normalized radar cross-section of the terrain. And that's what I've done here. One extra thing to try and work out is that not only did we generate the DEM for glaciological purposes, we built it to try and correct for the local instance angle of the radar onto the terrain. Because if you're correcting for the area averaged value, that area you're illuminating changes with the angle of arrival of the beam with the surface. And because we have a DEM, we can calculate that angle of arrival by just calculating the local normal at each pixel and then calculating the local instance angle. And by doing this, we calculate the normalized radar cross-section here of the glacier surface. And this is now calibrated, and it's coarser resolution because we implemented these corrections. But this now is the quantity of interest to try and understand what the backscatter characteristics of glacial ice is. And you can see it varies across the glacier surface. This is mainly because of the varying clutter environments that you get on the surface, meltwater streams, debris, different surface roughnesses. However, you can see that there are differences on the surface, which is here, the valley side, and this region here, again, different to the ice body in places. This region here, which is the margin of the ice, so this corresponds to this region here, slightly lower. And we think this could be because there was a high debris content in that particular area of the glacier, which suggests that if there's more debris, it lowers your backscatter value. And to try and put this into context with literature values of 94 gigahertz sigma naught normalized radar cross-section values, we've plotted here the histogram of sigma naught for that entire scene, and we've calculated a mean value of minus 15.9 dBs. And if you compare this to all these other values, okay, we've got volcanic terrain, soils, and sands, which soils tend to be slightly higher than glacier ice. But the biggest difference is between glacier ice and snow. So snow, dry, wet, and refrozen snow is all much brighter than ice. And this suggests to us that there is an opportunity here for terrain classification, which is going to be really useful moving forward to develop this sensor for glacier mapping purposes. So that's kind of everything I wanted to talk about today. But just to kind of hint on the future of this system, the pandemic has kind of scuppered a lot of our plans this year, but we do aim to go to Svalbard next year, hopefully, if fieldwork permits, if we're allowed to do fieldwork again. And we'll be measuring carving activity at the front of Handsbrain to try and showcase how well this instrument performs at gathering high resolution data. And we'll also be measuring snow, hopefully measuring snow this winter in the Cairngorms in Scotland. So I will be doing some Scotland fieldwork as well. And on that note, thank you for listening, and I guess I'll take any questions at the end.
Amazing, thank you, Will. I would suggest we do actually take the questions at the end, because when we do type them in the chat, we won't have them recorded on the video. So it might be quite nice to repeat Michaela's questions afterwards. But now over to Lauren. Lauren Vargo is a PhD. She finished a PhD last year at Victoria University in Wellington, and she's now a postdoc there. And she's mainly working on glacier monitoring glaciers in New Zealand. Lauren is also part of the IGS Egg that I just mentioned before. And another thing I really want to mention, Lauren has been involved in getting Girls on Ice started for New Zealand. I think that's a really cool thing to do, and I really hope it works out well. But now over to your talk, Lauren.
Awesome. Thanks so much, Rebecca. Can you hear me okay? Yeah, great. So this is work that, like Rebecca said, came from my PhD thesis, attributing extreme glacier mass loss to climate change. Yeah. So melting ice from glaciers is often used as proof of anthropogenic climate change. But it's not something that we do really formally know. So a lot of times when I've presented this work, people, like many scientists, they wonder if it's something that actually needs to be done, because we know that temperatures are rising, and we know that as temperatures rise, ice should melt more. But there is a real benefit to being able to formally show this link between melting ice and climate change. And that link has only been showed by one study previously. And that's really important. So if we look in this confidence plot here, when only one study is able to formally show a link between climate change and ice melt, that puts us in this low confidence box, because there's really limited evidence. So that's why it is important to have more studies that are able to attribute ice loss to climate change and using different methods. So the one study that has done this work before, that has shown a link, is the paper by Ben Marzian and others, where they showed that anthropogenic influence is influencing glacier mass loss around the world. And that's what this plot is showing here. So this is a plot from the paper. And we're looking at glacier mass balance modeled with the green line, shows without any human contributions to greenhouse gases. And the red line shows kind of climate as it is with humans today or over time. And so it's really important, as we can see the two lines diverge, I don't know, around 1990. And at that time, the black lines, which are measured glacier mass balance, they more closely follow the red line of modeled glacier mass balance with human influence. And so that was how Ben was able to show this link in his work. But that work looked at glaciers on decadal timescales. And that meant that some glaciers, particularly the ones in New Zealand, weren't able to be included because they don't have these long records of glacier mass change. So that led us to ask the question of whether we could attribute individual extreme glacier mass loss years to climate change. So to do that, we need measurements of glacier mass change. In New Zealand, there are two glaciers that have glaciological mass balance measured. One is Brewster Glacier, shown here. But then New Zealand has this really unique record of snowline changes. And so snowlines can be used as proxies for the equilibrium line altitude, which can then be used kind of as a proxy for glacier mass change. And so the snowline on a glacier, it's shown by this line here on this photo. And what makes it unique is you can visually identify it in photographs. So New Zealand has this record of over 50 glaciers with their snowline elevation varying every year since 1978. So we wanted to use these two different sets of measurements to see if we could attribute the years when New Zealand glaciers lost the most mass to climate change. And so the way that I did that was using extreme event attribution. And this is a pretty established method. It's been done for extreme climate events like heat waves, big rainfalls, or big droughts. And essentially the way that it works is it uses general circulation model simulations, so those simulations of climate around the Earth, for two different experiments. One is keeping greenhouse gas levels at pre-industrial levels, and we call that the natural world. And the other is the present world, and that's kind of the world that we're in today. So what climate is like with the greenhouse gases that have been emitted today. And so here's a plot that shows the results of kind of a theoretical plot that shows results like this. So this plot's looking at temperature distributions without climate change in the solid line and with climate change in the dashed line. And what's key is that with climate change, we see more extreme weather and more hot weather. And so I wanted to try and apply this method, but to glacier mass loss. So to do that, I identified the 2 years when New Zealand glaciers lost the most loss. That was 2011 and 2018, and that came from those snowline elevation measurements and the glaciological mass balance measurements. We then used a degree day model with an added radiation calculation so that it worked a bit better to simulate glacier mass balance. And our input were GCMs. We used 16 CMIT-5 GCMs, and that was to get at uncertainty between those different models that are part of CMIT-5. And then 34 members of the CESM large ensemble. So that's one model, but 34 different ensemble members to get at uncertainty within that one model. From all of those models, we use the historical natural run or the control run, and those are experiments that keep greenhouse gas levels at the pre-industrial. And then RCP 8.5 from 2006 to 2026, and that's pretty much to represent climate today or in 2011 and 2018, the 2 years that I'm looking at. And then we also used a New Zealand gridded climate data reanalysis, and that was to do a bias correction for the GCM output and the shortwave radiation, because we know that these GCMs, I think one grid box in some covers all of New Zealand, so that bias correction was really important. So here are the results. These are probability distributions of extreme mass loss in a single year for Brewster Glacier on the left and Rolliston Glacier on the right. So I'll walk through these plots. We see mass balance on the x-axis with more negative mass balances to the left. For both years, or for both glaciers, the present climate, so with human influence or with climate change, is in red. The bold line is the mean of all the simulations, with the shading showing the range of different models, different model parameters. And then the black is for natural climate, or the climate without humans. For both glaciers, the vertical dashed lines are the measured mass balances, with the blue showing the uncertainties in the measured mass balances. So for both glaciers, we can see, and for both years that we look at, we can see that there are higher probabilities of the extreme melt that was measured in 2011 and 2018. That extreme melt, there are higher probabilities of it occurring in the present world with humans compared to the natural world without humans. And so those specific numbers are down here for 2011, for Brewster Glacier and Rolliston Glacier, and 2018. So these are the same plots that I just showed, but now instead of looking at probabilities, we can calculate the increase in likelihood of this extreme mass loss occurring with climate change. So for Brewster Glacier, we see that there's an increase in likelihood of this extreme mass loss occurring because of climate change of at least 14 times. And in some simulations, it only occurred in the present climate, and that extreme measured mass loss didn't occur at all in the natural climate. For Rolliston Glacier, which is over here, that increase in likelihood is at least 6 times. And in some simulations, it was up to 190 times more likely to occur with anthropogenic forcing. And then, so those were the two glaciers with measured mass balance. Here are snowline elevations. So we were able to show that we were able to use the same method for snowline elevations. It didn't work quite as well. And that's because snowlines aren't a perfect proxy for glacier mass change. So now on all of these, this is 4 examples of glaciers where we use the snowline elevations. And now it's switched, so higher snowline elevations correspond to more glacier mass loss. And we can see that for all 4 of these glaciers, the present climate with humans is offset to the right of the distribution of snowlines for the natural climate. So for all of these glaciers, it's more likely that those high snowline elevations would occur with climate change than without. And so that's really what I've got. So the exciting part of this work was that we were able to develop this framework for calculating attribution of extreme glacier mass loss, both for mass balance and for snowlines, that proxy of mass balance. We're able to show that increases in mass loss were at least 6 times more likely in 2011, and at least 20 times more likely for Brewster Glacier in 2018. And that brings up, if we go back to this confidence chart, it brings us into this higher confidence, because now there's another study that agrees with the first one. It shows that there is human influence on glacier mass loss. So going forward, this in this work, we developed the framework, and that was kind of the big job, and applied it to 2 glaciers really in New Zealand. So I'm excited to apply it to the over 200 glaciers in the WGMS database that have mass balance measurements. We need at least a few years of mass balance measurements so that you can calibrate the degree day model. And yeah, I guess this will be really exciting, especially as we know glaciers in Europe had that huge melt year about a year ago. So it'll be interesting to look at the human influence there. But then I've also been thinking about how we could apply extreme event attribution to glacier length changes, and even to ice sheet changes. So if there are any ice sheet modelers out there listening who'd be interested in trying to apply this method to Greenland, let me know there, because that would be fun to work on. Yeah, so that's all I have, if you want to open it up for questions.
Amazing, thank you. So time for questions. If you type into the chat, we can unmute you, so you have the chance to speak. So I think we had a few questions from Michalea and Will. Yeah, so Jason Amundsen, I'll just unmute you so you can ask your question. If I'll find you.
He has to unmute himself, actually, Rebecca.
Ah, okay.
There we go. Thanks. Great talk, all of you. Actually, I really liked all 3 of those talks. My question was similar to, I think, Tim Bartholomew, and I forget who else. Someone else had a similar sort of question. We were wondering about where the velocities were sampled relative to the terminus of those glaciers, and then also, I guess my expectation was that you would see different spatial patterns in speed up, depending on whether the speed up is due to meltwater or due to changes in terminus position. So I'm wondering if that's something that could be resolved in the data and that might help explain some of the differences between the different glaciers and the different data sets.
Yeah, so you're absolutely right that it does depend on how far from the front I'm sampling velocities. I did test sites at about 10 different glaciers where I extracted velocities along a flow line and compared the seasonal amplitude and the timing of when you reach that seasonal maximum at like 5, 10, 15, 20 kilometers from the front. And in general, as you go further upstream, you have reduced seasonal amplitude. So you get more of that big swing closer to the front. And you can also, kind of like you mentioned, being able to partition meltwater-induced changes from frontal changes. You can also see that when it's a melt-driven acceleration, you kind of see it propagate downstream through time. So you'll notice the acceleration happens earlier in the melt season upstream, and then days later as you move downstream. So the timing of those peaks also varies. As far as incorporating that into looking at the categorical differences, everything, I haven't done all of that yet, but it is definitely something that will change within each glacier site through time, because of course you're having retreat at most of these glaciers. And I quickly just want to add that it's not just distance from the front. We're also seeing the amplitude is affected by patterns in thinning through time. And so glaciers that have thinned really dramatically and have reduced effective pressures, you actually see that it's almost like they have less room to accelerate, because now these glaciers are so close to flotation that the onset of melt water to the subglacial system, it has less upper limit to how much that glacier can accelerate. So you also see a competing reduced amplitude from thinning through time as well. So both things are really interesting to try to tease out.
Okay, nice. I think Lauren just put up a slide to advertise, because we forgot that, advertise next week's Speak before we all continue with questions just quickly, which is by Fima Stranero from Scripps Institute, with the title Ahoy Captain, Is That a Glacier Speed Up Ahead? So next week's seminar will be that. So I think we can continue with questions. We have one for Will from Sasha Leitman, if you would like to unmute yourself.
Yeah, I was just wondering, in terms of classification, whether you think that the difference between radar reflectance between ice and snow is significantly better for classification than the difference in optical properties in albedo from optical sensors like cameras.
Yeah, it's a really good question, and I guess almost impossible to tell unless you had both at the same place at the same time, because it varies so much. I mean, the ice that we were looking at did have quite a lot of debris at the top of it, and obviously different snow types vary. And those numbers I put on the screen were averages, and actually it's the range of values it could be. If your average is -10, you could have a range from -15 dBs to -5. So it's really difficult to say. I'm inclined to suggest that optical imagery would probably still be better, but as soon as you have cloud or rain, you can't use it. So that's obviously where we fit in. So I'm still inclined to say optical imagery is still going to be better for classifying between snow and ice, but the big advantage is that you can classify in bad conditions. Yeah.
Okay, we have another question for you, Will, I think, from Daniel Falaschi.
I mean, if it's not that, I can just read it out. Can you briefly name the most important advances, novelties of your radar compared to more familiar technologies, optical LiDAR sensors for glacier mapping? Yeah, it's basically, I mean, the resolution issue is the big one. The thing that maybe I was trying to get across was that millimetre-wave radar, it operates in that middle ground between low frequency radar systems. So the radars that are available at the moment, I mean, you've got the satellite Sentinel-1 and RadarSat, and then on the ground you've got the gamma radar. They all operate at 30 gigahertz and below, and then the optical systems, so those radar systems have a lower resolution. But then the optical systems, if you have bad weather conditions, which are abundant in glacier environments, then you can't image. So we try and sit in that middle ground where you can image in most weather conditions, but still gather data that has a high enough resolution that it's not quite as coarse as your lower frequency radar systems. Yeah.
Okay, amazing. We have a question by Anya.
Yes, thank you. Yeah, nice talk. Thank you so much. I was wondering, Michalea, if you looked at the subglacial geology, like, is it possible that there are changes in the subglacial geology that affect like what category those outlet glaciers are?
Yeah, so there was also a question sent to me by Bruce privately asking about hard beds versus till beds. Is that kind of what you're asking about as well?
Exactly. Yeah.
You know, I don't know enough about the differences in the bed properties across the ice sheet. I know that definitely probably plays a part in how these glaciers respond, but from the couple of papers that I've looked at, some areas it's pretty ambiguous whether it's a till or hard bed. So I'm sure that plays a part, but I haven't integrated estimates of bed properties into the different categories yet. No.
Yeah, it would be interesting to look at the surrounding geology from just like geological maps.
Yeah, and you know that you're probably like the third or fourth. Yeah, and enough people have mentioned it to me now that I think it is definitely something I need to incorporate. So yeah, thank you.
Cool, awesome.
Okay. Any more questions? I think we've answered everything from the chat. I guess Andre Bliss asked to Michalea and Will, how are you generating your Landsat time lapses?
Yeah, you go first.
Well, the time lapse I showed, I think it was at Jakobshavn Glacier, was from the internet. I didn't make that one myself, but the time lapses that I have made just from compiling downloaded Landsat images that are publicly available, and I make them in MATLAB, but I'm always open to hearing if someone has a better platform for doing that. I don't know if Will maybe have a more streamlined process.
I definitely don't have a streamlined process. I use the internet. I use the Sentinel EO browser, I think it's called. So then you can download anything from Sentinel-1 to Landsat. That's probably it. And then you just put in the dates, choose your cloud cover percentage, and you can just make it on the spot. It takes, once you get used to it, you can do it in about 5 minutes. It's really nice. And now that I found it, if anyone follows me on Twitter, then I'll be probably putting up loads.
Okay, any more questions? Okay, I don't see anyone raising the hand or anything. Well, that was really amazing. Thanks to all the 3 speakers. That was really good. We had lots of thank yous and amazing talks and clapping hands. So that was really great. Well, I'm looking forward to seeing you all next week for next week's talk.